At 5:32 in the afternoon, on the 29th of August, 1907, the longest bridge span ever attempted fell into the St. Lawrence River. 19,000 tons of steel went down in about 15 seconds. 86 men were working on it. 11 came home. 6 miles away, in Quebec City, people felt the shock come up through their floors and assumed an earthquake had hit. The bridge crew still had 13 minutes to work before the whistle. Every stress in that steel had been approved by the most respected bridge engineer in America. He was about 500 miles away. He hadn't set foot on the structure in 4 years. That very morning, from his office in New York, he had wired the fabricator to put no more weight on the bridge. Nobody stopped the work. This is the Quebec Bridge, the worst construction disaster in the history of bridge building, and the holder of a world record that has never been beaten. It's the story of a structure that worked perfectly on paper in an office 500 miles from the river. On paper, nobody ever rechecked. Quebec City sits where the St. Lawrence narrows, and for 2 centuries that river cut the city off from the south shore. Ice shut the ferries down for months every winter. The Quebec Bridge and Railway Company was chartered to fix that, and it was poor from its first day. It held a charter, a site, and almost no capital. So when the company ran a design competition in the 1890s, the deciding question was never what's best. It was what's cheapest. The man brought in to judge the entries was Theodore Cooper of New York. Cooper was an American civil engineer with an unblemished record and enormous professional standing. He'd graduated from Rensselaer in 1858, served through the Civil War in the Navy, and inspected the Eads Bridge at St. Louis, the first great steel bridge built in America. Cooper's system of railway loadings was used right across the continent, so most American bridges of that era were designed to a standard carrying his name. He called the Phoenix Bridge Company's proposal the best and cheapest plan submitted to him. In November 1900, he became the project's consulting engineer. That appointment made him the final authority on every drawing. The fabricator was the Phoenix Bridge Company of Phoenixville, Pennsylvania, whose designing engineer, Peter Slapka, did the actual calculations. So Phoenix checked Phoenix's work, Cooper checked Phoenix, nobody checked Cooper. In May 1900, Cooper had recommended stretching the main span from 1,600 feet to 1,800. The longer reach would put the piers on better ground and spare the company the cost of deep foundations. It would also make this the longest cantilever span on Earth. The record it would take belonged to the Firth of Forth Bridge in Scotland, whose 2 spans measured 1,710 feet. Quebec would beat that by 90 feet. But the Forth Bridge had been deliberately overbuilt because Britain had just lost a bridge and a train in the Tay disaster. Quebec's bridge would be nothing like that. 1,800 feet between the piers, a deck 150 feet above the water, main posts 315 feet tall, weighing 350 tons apiece. It would carry heavy railway traffic, and it would be lean. That steel would be raised by riveting gangs, and the finest of them came from Kahnawake, the Mohawk community across the river from Montreal. They'd taken up the trade in 1886, when a railway built a bridge onto their land and hired them as day laborers. Instead of staying on the ground, the men climbed. By 1907, more than 70 Kahnawake men were experienced bridge workers, sought after not as spare hands, but as specialists who could work at height, in wind, on steel that moved under them. On the Quebec Bridge, 38 of them were on the payroll. In June 1903, Cooper issued his specifications, and they were aggressive. He cut the design wind pressure to 30 pounds per square foot, where the Forth Bridge had used 56. He raised allowable working stresses as high as 24,000 pounds per square inch, against a common practice near 16,000. Nobody objected. The Royal Commission would later record that the unit stresses were higher than any established by past practice, and that the specifications were accepted without protest by all interested. Hold on to that phrase. Not one party in the chain pushed back. Cooper was 60 when he took the job, and his health was failing. After May 1903, he never visited the site again. The largest span on Earth was now supervised from a desk in New York, by letter, by telegram, and by the reports of men he could not watch. Ottawa saw the gap. The government's chief engineer wanted an outside engineer hired to check Cooper's plans, with final authority over them. Cooper objected strongly. So did the bridge company. So did Phoenix. The minister backed down. From that day, the bridge's only safeguard was one man's judgment. Here's the strange part. The arithmetic wasn't wrong. Slapka's stress calculations were carried out competently by a capable engineer at a first-rate company, and they would have been right, for a different bridge. Every figure was correct. One of the inputs belonged to a structure nobody built. A bridge carries two kinds of load. Live load is the traffic, the trains, the wind, the snow. Dead load is the bridge itself. Every plate, every rivet, every pound of steel holding up the rest of the steel. On a span this long, the bridge is mostly carrying itself. When Cooper stretched the span by 200 feet, the dead load grew with it. It had to. But the dead load figures used to design the anchor arm were preliminary numbers worked out for the 1,600-foot bridge, and they were carried straight across into the 1,800-foot design. The anchor arm drawings were approved in October 1904. Erection began in July 1905 on false work at the South Shore, and steel went up through 1906. Then, as the real fabricated weights came in from the shops, Slapka worked out that the bridge was coming in heavier than his design had assumed. He told Cooper. Cooper's own account of that moment survives in the inquiry record. There was no means of changing or correcting the work, he said. He put the increase in stresses at about 7%, judged that 7% was not fatal, and told Slapka they would have to submit to it. That is the hinge of this whole story. The error was found in time, not by an inspector, not by an inquiry, but by the designer himself while the bridge was still going up. And the response was to carry on because too much of it already stood over the river. The Royal Commission was blunt about what that meant. A grave error was made, it wrote, in assuming the dead load at too low a value, and not afterwards revising this assumption. That error alone, the commissioners found, was of sufficient magnitude to have required the condemnation of the bridge. You'll hear this story told as a morality play. One famous old engineer, too proud to admit a mistake and too vain to be corrected, kills 75 men from an armchair in New York. It's a satisfying version. It's also doing about half the work it claims to do. The fatal number wasn't Cooper's. It was computed in Phoenixville, approved in New York, and re-examined by nobody because that job belonged to no one in the arrangement. The client couldn't afford delay. The fabricator was marking its own homework. Cooper held all the authority and had no auditor. Now look at what actually broke. The lower chords of the anchor arm were compression members, the pieces being squeezed rather than stretched. Chord A9L wasn't a solid beam. It was tall steel ribs, built up from plates over 4 feet deep, stitched together with lattice bars and rivets. Nobody in 1907 truly understood how a member like that behaved under enormous compression. No machine on Earth could load a full-size Quebec Bridge cord until it failed. The working rules were extrapolations from small laboratory columns, stretched far past the evidence behind them. The Commission's own consultant, the American engineer Charles Schneider, put his finger on it. The cord's parts weren't tied together properly. The latticing wasn't strong enough to make them share the load, so each rib could wander alone. A cord could satisfy every rule of 1907 and still fold. So, a bridge carrying weight it wasn't designed for, through members nobody knew how to design, under a specification nobody had challenged, with no one empowered to stop it. On paper, all of it worked. In the summer of 1907, the steel began to disagree. The first person to see it was the most junior man in the chain. Norman McClure was the inspecting engineer on site for the Quebec Bridge Company. Young, careful, and by the surviving record, right about everything. In June 1907, he found 2 chords in the anchor arm a 1/4 inch out of line. The version everyone repeats is that the bridge came down out of nowhere. It didn't. The warning ran for 3 weeks. in ink, and every page of it went into the Royal Commission's files. You can still read the entire argument today in the order it happened. On the 6th of August, McClure reported bent lower chords in the south anchor arm. Cooper's reply was almost plaintive. How did that happen? Steel rolled straight and riveted into a bridge is not supposed to quietly acquire a curve. Phoenix's people on site had an explanation they preferred. The chords must have arrived bent from the yard, they said, and one of them genuinely had been dropped and damaged back in 1905. The superintendent believed it. The erection foreman didn't. The argument ran on for weeks in letters and telegrams. Work paused briefly, then resumed. The reason survives in a note from the bridge company's chief engineer to Cooper. Holding up the work would have a very bad moral effect on all concerned and might stop the job for the season by losing the men. The season was short. The money was shorter. On the 27th of August, McClure measured again. A rib that had been 3/4 of an inch out of line 8 days earlier now stood 2 1/4 inches out. He wrote to Cooper with sketches, and he was certain. Their present shape was undoubtedly due to the stress they were now receiving. There was a telephone at the site. McClure got on a train instead. His measurements, his sketches, and his conviction all traveled south at the speed of a passenger service, which is how the warning about the largest bridge on Earth actually moved. Meanwhile, the bridge kept being built. On the morning of the 29th, McClure reached Cooper's office in New York, and Cooper finally grasped how serious this was. He wired Phoenixville at once. Add no more load to the bridge till after due consideration of the facts. The telegram arrived in Pennsylvania. It was read. And nothing happened. Phoenix's chief engineer held it in his hand, and the decision was to wait for the morning when McClure could explain in person. Nobody wired the site. Nobody telephoned the erection crews. Since 7 that morning, the men at Quebec had been out on the steel. There were about 86 of them out there. Riveting gangs on the anchor arm, hoisting crews further out, the big erection traveler parked at the end of the cantilever. 3 panels of the suspended span already hung in the air. Every hour of work put more weight onto cord A9L. Around 4 o'clock, Alexander Beauvais, a Kahnawake riveter, found that a rivet he had driven an hour earlier had sheared clean through. He reported it to his foreman. He was told it was nothing serious. He walked back out onto the span. At 5:32, cord A9L folded. The load jumped instantly to its twin across the bridge, and A9R folded too. With both lower chords gone, the anchor arm had nothing left to stand on. The south half of the Quebec Bridge went into the river in about 15 seconds. The timekeeper, a man named Huot, was seconds from blowing the whistle that ended the day. He ran, and the last girder let go behind him as he reached solid ground. Alexander Beauvais rode the steel down into the wreck and survived it with broken bones. Of the 86 men on the structure, 75 were killed. Other careful sources say 74 or 76. 11 lived. What was left went into the channel in a tangle of steel that took 2 years to clear, and the recovery of the dead was slow, dangerous, and in many cases, simply impossible. 38 Kahnawake ironworkers had gone to that job. 33 of them died on the 29th of August. Some accounts say 35 because casual labor was counted loosely in 1907. In one small community, in one afternoon, that came to 24 widows and, by Kahnawake's own count, 53 children left without fathers. The youngest was 18, the oldest was 44, a man remembered as Sosi O'Ree, who left 11 children and a wife expecting a 12th. In the Kahnawake cemetery, the ironworkers' graves are marked with crosses cut from lengths of steel girder. What Kahnawake did next shaped the century that followed. The women of the community ruled that their men would never again all work a single job. They would spread across separate contracts in small gangs so that no one accident could ever take a generation again. That rule sent them wherever steel was rising, and by the 1920s that meant New York, where Kahnawake families settled in Brooklyn and their men walked the high iron over Manhattan. A safety rule written in grief helped raise the skyline of another country. Back at the river, Ottawa wanted answers. 2 days after the collapse, the government appointed a royal commission: Henry Holgate of Montreal, John Carey of Ontario, and John Galbraith, Dean of Engineering at the University of Toronto. They could compel testimony and documents. Their report ran past 200 pages, with 21 appendices behind it. It appeared in February 1908, and it did not flinch. The collapse resulted from the failure of the lower chords in the anchor arm near the main pier. The failure of those chords was due to their defective design. The design was Slopka's. The approval was Cooper's. Then comes the sentence people remember: the failure cannot be attributed directly to any cause other than errors in judgment on the part of these two engineers. But read the finding immediately after it. Those errors, the commissioners wrote, came from neither ignorance nor neglect of duty, nor any desire to economize. The ability of the two engineers was tried in one of the most difficult professional problems of the day, and proved insufficient for the task. That's a verdict on a system, dressed as a verdict on two men. The commission named the men who signed, then described an organization in which nobody could stop the work. The last thing people say about this bridge is that nothing changed afterwards. That one is badly wrong. Ottawa took the project over outright, and the replacement was designed by a board of engineers, a Canadian, a Briton from the Fourth Bridge, and an American, required by mandate to check each other. The second Quebec Bridge kept the 1,800-foot span and threw weight at everything else. Nickel steel, a stiffer K-truss, chords built as proper closed sections. It was heavier, uglier, and beyond argument, strong. Then, on the 11th of September 1916, they went to lift the middle of it. The center span was a separate structure, 640 feet long, 5,000 tons, floated out on scows and jacked up towards both cantilever arms. Thousands of spectators lined the shores to watch. Minutes into the lift, a casting in the lifting gear at one corner fractured. 1,200 tons at that corner jumped onto what remained, crushed it, and the corner dropped. The span twisted off its supports and went into the St. Lawrence. 13 men were killed. 2 days later, the contractor publicly accepted full responsibility for the failure and began building a replacement span. And there's the irony that belongs in this file. The permanent structure had been checked to exhaustion by exactly the independent regime the first disaster created. What broke was a casting in the temporary equipment used to lift it. The scrutiny had moved, the gap had moved with it. A new center span was raised successfully on the 20th of September 1917, and a ceremonial train crossed that October. Theodore Cooper died in New York in August 1919. The same month the finished bridge was formally dedicated. He was 80 years old. The bridge is still standing, 1,800 feet between the piers, still carrying rail and road traffic across the St. Lawrence. More than a century on, nobody has built a longer cantilever span. The worst disaster in bridge construction and the standing world record are the same structure. One more story, and it's the one you have almost certainly heard. Canadian engineers wear an iron ring on the little finger of the working hand, and the legend says those rings were forged from the wreckage of this bridge, the metal itself worn as a lifelong reminder. The ritual is entirely real. The ritual of the calling of an engineer was proposed in 1922 by Herbert Haltane, a mining professor at the University of Toronto, with an obligation written by the author Rudyard Kipling. The first ceremony was held in Montreal in April 1925 for 6 engineers. But there's no documentary evidence that any ring was made from Quebec Bridge steel, and the body that runs the ritual has never claimed there was. The story attached itself later because it feels like it ought to be true. That instinct, that the metal should remember, is deeply human. What this disaster built was a habit, independent review, checking the checker, a profession that stopped accepting one towering reputation as a substitute for verification. The Quebec Bridge didn't fail for want of a genius. It failed for want of a second opinion. And now you know the real story of the Quebec Bridge, a world record and a graveyard in one structure. Ask who checks your work. We hope you enjoyed this episode and learned something new along the way. And as always, stay curious, stay careful, and remember, every failure is a lesson somebody paid for.